Hello guys, welcome to the YouTube channel. Today in this video I will try to cover some introduction to circles and theorem 10.2. Okay, now what is a circle? In the class 9 we have studied the definition of circle, that is the collection of all the points in a plane which are equidistant from the fixed point. What is that equidistance and what is the fixed point? Is that so it is a collection of all the points in a plane. It is a collection of all the points in a plane which are equidistant from the fixed point. Fixed point is called as the center of a given circle. Okay. So from the center of a given circle, if you measure the distance of any point, it is all same only. Okay. That distance we call it as a radius of a circle. Okay. This fixed point is called center, and the distance between this fixed point to any point on this circle is called as the radius. And in the class 9 we have studied the terms related to circles also, like radius, diameter, segment, sector, okay, and so many we have studied. But in this circle chapter we are mainly concentrating on the tangents and secants on the circle. Okay. Now let us examine different situations that arises whenever a given line and a circle are given. Okay, when a line and circle are given, what are the possible ways to indicate the line and circle? Okay, so let us have first let us consider first case where a line and circle are drawn in this way. Okay, so in this case, first case, this line, AB line, is we can say it is a non-intersecting line with respect to the circle. Okay, so this is the line which is not in contact with the circle, and hence it is called it is not intersecting line with respect to a circle. In the second case, I can draw a circle and a line in this way. Okay, this is called AB line. Okay, and this line is intersecting the circle at two different points, say P and Q. Okay, so this is called as the secant. Okay, whenever the line which cuts the circle into two different points, then we can say this line is called as secant line. Okay, and one more case is that when a line is drawn in this way by taking only one common point, okay, only one common point, then this line AB is called as the tangent with respect to the circle. Okay, whenever a line and circle are given, so you can indicate them with three possibilities. One is in this way, this is non-intersecting line with respect to the circle, and this is intersecting at two distinct points, hence we can say this AB line is called as the secant line. This is called secant line. And when the line touches the circle at only one point, we call AB line is the tangent to the given circle. Okay, so tangent to the given circle. Understood the difference between a tangent and secant? Whenever a line is drawn which intersect the circle at two different points, then that line is called as the secant line. When the line touches the circle at only one point, we call them as a tangent to the given circle. Okay. Okay, the next question is how many parallel tangents can be drawn for a given secant line? Can you answer? How many parallel tangents can be drawn for a given secant line? Okay, let us consider a circle first, and I will draw one line. So this line we can call it as secant line because this particular line, AB line, which is intersecting the circle at two different points. No matter where it is intersecting, but if it intersects at two different points, we call them as a secant line. Okay, with respect to this secant line, how many parallel tangents are possible? As I said, tangent is nothing but it is a line which meet the circle at only one point. Okay, so I can draw at the boundary only. That is the only possibility, because we cannot draw a tangent in this way within the circle. So it should meet the boundary of a circle only. So I can draw in this way, one circle in one line in this way. This is called as tangent, and one more tangent I can draw in this way. So I can draw in this way. This is also a tangent which meeting the circle at only one point, and this is also a tangent which is meeting at one point. Okay, so here only two parallel tangents we can draw for a given circle, given secant line. Okay, only two tangents are possible. That is called parallel tangents. Okay, how many parallel tangents are possible for a given secant line? Only two is the correct answer. Okay, one more question. How many parallel tangents can be drawn on a circle? So just see the difference between earlier question and this question. Earlier question was how many parallel tangents can be drawn for a given secant line? That is, only two parallel tangents are possible. But here, how many parallel tangents can be drawn on a circle? So you can draw infinitely many parallel tangents. You can draw in this way. This is one set of parallel tangents, and you can draw in this way. This is another set, and you can draw as many as possible. So you can say infinitely many tangents, that is parallel tangents, are possible on a circle. But when the question is how many parallel tangents can be drawn for a given secant line, that is only two parallel tangents are possible. Okay. Okay, the next concept is number of tangents from a point on a circle. So let us determine how many tangents are possible by considering these three cases. Okay, the first case is when the point is inside the circle, how many tangents are possible? Okay, let us consider a circle, and I am considering one point inside the circle. See, when the point is inside the circle, how many number of tangents are possible? So is it possible to draw a tangent by using this point? Okay, is it possible? No, right? Because we can draw infinitely many secant line, right? We can draw infinitely many secant line through this point, but a tangent we cannot able to draw. Hence, you can say there is no tangents possible in this case. No tangents possible. No tangents is possible when the point is inside the circle. Okay, but we can draw infinitely many secants possible, but tangent is not possible, right? Okay, when the point is on the circle, when the point is on the circle, how many tangents are possible? So as I said, there is only one common point between a line and a circle. That line is called as a tangent. So here I can draw a tangent like this by using this point. Okay, this is called as common point, right? But from this point, is it possible to draw some more tangents? Not at all possible. Only one tangent is possible when the point is on the circle, right? But if you consider another point, we can draw one more tangent. If you consider here, one more tangent. So there are infinitely many tangents are possible on the circle, but for a given point on the circle, only one tangent is possible. Got the difference? Okay, you can draw infinitely many tangents by taking many different points, but for a single point, there is only one tangent is possible. Okay, you write here, only one tangent is possible. Only one tangent is possible when the given point is on the circle, right? In the same way, when the point is outside the circle, how many tangents are possible? Okay, let me consider the point here. which is outside the circle. Then how many tangents are possible? We can draw two tangents. One is here and another in this way. Another in this way. Okay. So only two tangents are possible, right? When the point is outside the circle, this is very important. When the point is outside the circle, there are only two tangents possible. Got it? When the point is inside the circle, no tangent is possible, but infinitely many secants are possible. But when the point is on the circle, only one tangent is possible. But when the point is outside the circle, there are two tangents possible. One is this, another is this. Fine. Okay, here is the theorem 10.2. The length of the tangents drawn from the external point to a circle are equal. So here we need to prove that the length of the tangents drawn from the external point P to the circle are equal. That means we need to prove the length of the tangent, that is PA, is equal to the length of the tangent PB. So these two are equal, we need to prove. Okay, let us see how to prove this. First we will have construction. Okay, just now I said that when the point is lying outside the circle, there are two tangents possible. Okay, in this theorem we are proving that those two tangent lengths are equal. Okay, okay, construction is, let's join the points. Let's join O to A, O to point B, and O to point P. Okay. Okay, now we already know that from the theorem 10.1, that is the angle between the radius and the tangent are 90 degree, right? The angle between these two is 90 degree, angle between these two is also 90 degree. Okay, now we will consider the two triangles OAP and OBP. Okay, in the proof we will consider two triangles OAP, triangle OAP and triangle OBP. Okay, we know that it is 90 degree. So by using RHS we can prove this. How? Because one is already 90 degree, in this triangle also 90 degree, and in this triangle also 90 degree, and opposite to right angle is always a hypotenuse. Okay, for example, if this is a ABC triangle and if I consider 90 degree here, its opposite side is hypotenuse. We already know that hypotenuse is a common side, right? OP side is common to both the triangles. Okay, OAP and OBP, OP is a common side and that becomes the hypotenuse in this case, right? So 90 degree hypotenuse, and one side is equal because the OA and OB are the radii of the circle, right? So by using RHS we will try to prove that these two are congruent, right? If these two are congruent, then by using CP/CT we can write PA is equal to PB. That is what we needed to prove, right? Okay. So first I will write the angles OAP is equal to angle OBP. Okay, in the triangle OAP, angle OAP, in the triangle OBP, angle OBP are equal because they are 90 degree each. Okay, and also we can write this is a right angle. Next, OP is equal to OP. OP is equal to OP, right? Because common side. This is the common side in both the triangles. And we can write this as hypotenuse. And next is OA in this triangle, OB in this triangle are equal. OA is equal to OB because OA and OB are the radii of a circle. Radii of a circle. And we can write this as yes. Okay, now by RHS congruency rule, we can write that triangle OAP is congruent to triangle OBP. Okay, and if these two triangles are congruent, see OAP triangle and OBP triangle are congruent, then we can write PA is equal to PB, because when the two triangles are congruent, their corresponding angles, corresponding sides, everything will be equal. That is why I can write PA is equal to PB by CPCT, corresponding parts of congruent triangle. Hence, this is what we needed to prove, and hence it is proved. Okay.